Hello everyone and welcome to this new week about functional programming in OCaml. In the following 2 weeks we will come back on types and in particular how you can structure your code and your data using types. This week we will first learn how to define our own types, and to do so you will need several ingredients: tuples, records and arrays. Finally, we will use them in order to program a small typed database. A primary usage of types is to document your code in order to explain to other programmers how you use primitive type in order to encode some specific form of information. For example, you may want to encode the day of the week by choosing 0 to represent Monday, by choosing 1 to represent Tuesday, and so on. And so what you get in the end is a subset of int. And maybe you want to name this subset using a type identifier, so that you can carry an informal invariant that an integer x is a valid day if it is between 0 and 6. Then you can use this type identifier in the types of a function that must work on the day of the week, so that you can document the fact that not every integer can be used as an input of this function, but only integer between 0 and 6. So we will now see some examples of type definitions. So let us consider the definition of a type for color. We will write this definition saying that a color is represented by an integer. And after that, we can declare the red to be a color by using the colon followed by the name of the type we want to assign to this identifier, which is color. And then we can just use 0, which is an integer, to define the red. And of course, we can do that to define many colors. So now let us define another type abbreviation for positive integers. Again, it just means that we will introduce a name for a type for positive integer, but it will be equal to integers, the ones that we already know. Now imagine that you want to implement the absolute function that turns a positive or negative integer into a positive integer. You may want to document that fact by saying that it takes an argument which is an int, which can be positive or negative, and the fact that you return minus x when x is less than 0 and x when x is greater than 0 means that the result of this function, of this expression, is a positive number. So we have assigned a type to a sub-expression. In fact, we can also assign the type to the return of a function, just by using colon followed by the name of the return type just before the equal sign. And we got exactly the same answer from the top level. So now that we have seen several examples of user-defined type definitions, let us review the general rule for the syntax. You have to use first the keyword type, followed by a type identifier that you have chosen, and then after the equal sign, you just have to write the type definition. So we say that this new type identifier is a synonym or an abbreviation for some type. The identifier must start with a lowercase letter. For the moment, we will only use the primitive types that we know for some type: int, bool, string, char, and float. But we will discover several new type constructions soon. After you have introduced a new type identifier, you can use it to constrain an expression or definition to be of some type. This is called type annotation. So to annotate an identifier with a type, you use a colon, and just after the colon, you write the type you want to assign to this identifier. If you want to annotate a function argument with a type, you just use a parenthesis, the name of your argument, and a colon, and after that, the type that you want to use for x. You can also constrain the return type of a function by using a colon and the type of this return type just before the equal symbol. In general, you can constrain the type of any sub-expression of your program. To do so, you use parentheses around this expression, and just before the closing parenthesis, you add a colon with the type that you want to ascribe to this expression. You have to understand that in OCaml, types are static, which means that they do not have an impact on the program execution. This means that when you have a type t which is equal to int, and you have an x of type t, then this x is also of type int, which means that a value of type t is represented exactly as the value of type int in the machine. Now, what kind of programming errors that you can do when you use your own type definitions? The first one, the most common one, is when you interact with the OCaml top level and you have chosen the same type identifier for several definitions. In that case, we will see in the following example that you can get very weird error messages. So let us first define a type t, which is equal to int. And right after that, a definition for the identifier x of type t, which is equal to 0. And now, a type t, which is equal to bool. So I have reused the same name as the one of my previous type definition. This name can be used in the definition of a function that is expecting a value of type t. For instance, to apply the not function to this argument. Now, if I apply f to x, then, of course, this is invalid because this x has indeed a type t, but this is the first version of the type t, while f is expecting a value of the second version of the type t. Indeed, you can notice that OCaml shows you the number of this version that is using internally to distinguish between these two types. There is another kind of error that you can do when you use type synonyms. It's more a semantic errors. For instance, if you have introduced a type for positive integer like this, you have to understand that this name positive is only a documentation, and you do not have a static guarantee that every value of this type is actually a positive integer. For instance, you can perfectly write the following definition saying that x, which is equal to -1, has type positive, because -1 is an int, so this definition is accepted by the type checker. Fortunately, the OCaml type system will help us define more precise types in order to be able to capture that kind of properties statically.